Good afternoon, everyone. My name is George McElwraith. I'm currently the chair of IIRSM in Scotland. Before we say anything more, it's good to see that we've now got a refreshed committee in place, and the first meeting of that committee will be tomorrow afternoon, in fact. I hope that things can now begin to move fairly quickly. Today, our speaker is Nick Bramwell. Nick is a consultant and owner of SafeArc Solutions. Nick qualified as an electrical engineer and power station specialist. Before we had started today, I was talking to Julie and I'd said that I was a specialist in power stations as well, but the opposite end of the spectrum from where Nick was. I was in the dirty end where the coal went in at one end and came out as electricity at the other. His background has been that he's been in the brownfield oil and gas sector for many years. He trained with Jim Phillips, who is a worldwide expert on electrical arc safety. Previously, he has worked in the oil and gas installations, water treatment plant, and many other large industrial sites. Without any further ado, I'm going to hand over the rest of the presentation to Nick. It's all yours, Nick.
Thanks very much, George. Yeah, good afternoon, everyone. Thank you very much to the IIRSM Scotland branch for hosting this webinar, Julie for all the organisation work, and thank you everyone for joining. Hopefully you can all see my slides, so without further ado, I'll make a start. So over the next 40 or so minutes, my aim is to show you what we mean by an electrical arc flash, discuss how it fits into health and safety legislation, particularly here in the UK, and demonstrate how by undertaking a risk assessment and putting in place some sensible mitigations, we can improve worker safety and reduce the potential impact for equipment damage and downtime. I'd like to frame this discussion by describing a bit of an arc flash incident, and then I'll revisit that at the end to show how by making some simple changes at site, you can bring about a reduction in risk to people. So I'll start off with that incident. So it's late afternoon on a Friday. People are busy talking about their weekend plans. It's really been a very hectic week. It's probably the busiest of the year on site, with a major outage on the compressor house. There's been a whole bunch of inspections and maintenance activities and all that kind of stuff has been carried out, and that's all finished now. So really all that remains to be done is to get the compressor house itself powered back up. You head down to the main substation on site. From here, there's a 415 supply which goes along to the compressor house. So to get that back energized, the circuit breaker needs to be racked in and closed up. You're the site health and safety advisor, and earlier in the day, you sat in on a permit meeting for restoring the power. It all sounded fairly straightforward. This is something that's done a handful of times a year on site, nothing particularly out of the ordinary. A task risk assessment has been completed, but nothing unusual came up. Talked about electric shock, talked about the idea of slips and trips in the substation, talked about making sure whatever other activities were taking place that they were accounted for, and everyone was happy with that. So when you arrive down at the substation, there's a couple of your electricians, Scott and Sam, standing in front of the switchboard, ready to rack this breaker back in. A bit of maintenance and work had been done on the breaker, but again, nothing out of the ordinary. It's all been tidied up, and now it's just a case of getting this breaker back into the switchboard and closing it up to power up the compressor house. You have a quick chat with Sam while Scott completes some final paperwork, and then you stand back to let them get on with the task. They position the breaker into the cubicle, and then Sam takes a step back. Scott's going to be doing this. He pushes it slowly forward into the slot. It looks like everything's going well from where you're standing a little further back, but then there's a snag, and the breaker stops slightly short of its home position. There's a couple of moments of looking, scratching heads, and someone working on the other side of the switch room shouts, "Put your back into it, Scott." He gives the breaker a hard shove, and it moves backwards. But just then, there's a bright metallic ping. It's quickly followed by a huge explosive sound, and you shield your eyes as white light erupts from around the breaker. This is quickly followed by a wave of flames and black smoke that engulfs Scott and Sam standing right in front of the switchboard. You stumble backwards as the heat from the blast builds, In a panic, you're running to find the alarm call point at a phone. So what just happened? Well, somewhere at the back of the switchboard behind the circuit breaker, there's copper bars which are energized. This is what the circuit breaker is ultimately going to connect into. And this top set of bars coming down from the switchboard is energized because the rest of the switchboard is live. De-energizing that switchboard is going to cause too much disruption on site. As the breaker was being racked in, somewhere in the mechanism, a metal piece that had come loose during maintenance broke off, and it pinged across these copper conducting bars at the back of the panel, which are, as I say, alive. It briefly bridged the gap between these three conducting phases, and this is what sets off the arc flash. A very high current flows through the metal piece, acting as a short effectively between those conducting parts. The metal piece is probably flung clear at this point by the forces involved, but the high fault current continues to flow. It had ionized the air between the conductors and using this as a conducting route. There's nothing to constrain this arc which forms, and it gives off a huge amount of heat, releasing huge amounts of thermal energy, which basically vaporize anything close by, metalwork, copperwork, parts of the switchboard, and starts producing toxic fumes and a rapidly expanding series of gases. This is going to force, the pressure is going to force that breaker forwards towards the electricians, and that allows this cloud of heat and vapors to be released into the switch room, engulfing them. From your perspective, a little bit further away, the event felt like it lasted a lifetime, but in reality, it's probably only going to be a second or so before some overcurrent protection device somewhere detects the high current and trips, extinguishing the arc. So let's have a look at what does arc flash look like in a bit more detail. It's very difficult to capture on camera. It's unpredictable. It's over almost as soon as it's begun. So some of the best footage we have is from laboratory testing. This is often conducted as a way of verifying arc flash PPE. So we have a lot of good imagery from this kind of thing. Here's one such example showing an arc flash occurring on a low voltage switchboard, which is similar to that discussed in the incident. It's filmed in slow motion. We see molten metal flying towards and past the dummy's face at the top, and then we see this rapidly expanding ball of flame and vapors that starts to wrap around the figure. So this is an arc flash. Here's another example from laboratory testing with a small electrical panel on the right-hand side, and again a very dramatic event with releases of molten metal and this production of flame and toxic vapors. There are some examples floating around on the internet of people capturing arc flash incidents going on. Here is one such example in an industrial setting. It appears to be an arcing incident on actually a closed up piece of control gear. But here you can see that even with the covers in place, you can see how energetic it is. And again, we've got hot metal, we've got toxic fumes being released. And again, this arc continues for quite some time. It's really going to be futile trying to do anything with fire extinguishers in this situation until the arc itself is extinguished. And one final video example, this is from a cotton processing plant in America. On a low voltage switchboard, the one that's circled on the right hand side of the image. And if I play the video, this starts off with a series of kind of explosive booms over at that switchboard. And as the person filming it moves across to see the incident, you see this is a very dramatic release of energy. Again, molten metal. Presumably someone was actually working on this because the switchboard door is open. And we've also got flames and again, the toxic fumes being released. You can see the different responses from people to this. Some people wanting to get closer and film it, and some people just trying to get out of there as quickly as possible. That would certainly be my reaction. So you can see that the arc flash is a very energetic event. And so what does that mean in terms of the risk to people and the risk to equipment? Well, of course, as you've seen by that, arc flash can cause, with the energy involved, arc flash can cause serious injuries. In the worst case, it could lead to the death of someone who's standing right in front of that equipment. The thermal energy released means that serious burns are inevitable. with normal protective clothing liable to catch on fire or even start melting. The arc event is so energetic that it can lead to damage to sight and hearing, and the release of shrapnel has the potential to cause cuts and puncture wounds. So here's a couple of examples from newspaper stories. Arc flash occasionally kind of makes it into the headlines. This one on the left from the Northern Echo reported on actually 2 separate arc flash incidents over a couple of years at the same mining site in the northeast of England. But one such incident involved an electrical worker tidying up inside a live high voltage panel, and unfortunately brought a vacuum cleaner nozzle into contact with the live conductors. So here we've got that inadvertent contact with the live conducting part, setting off an arc flash event. Thankfully he survived, but he suffered from terrible burn injuries, requiring 2 weeks of intensive care in hospital, numerous skin graft operations to repair deep burns to his face, hands, and his torso. And sadly, those injuries have proved to be life-changing. He's no longer able to do that previous role, and he's had to move into an office-based role. He just can no longer do what he used to be doing. And in a news story from on the right-hand side from maybe a few years ago, but a little bit closer to home for us here in Scotland, on Tayside, an electrician who was working in Dundee experienced an arc flash after opening a panel. And unfortunately, there were live conductors right behind, which he wasn't expecting. The metal panel was touched to the live conductors, and this set off an arc flash. It was midwinter at the time, and a site supervisor used snow to try and cool the burns to the electrician whilst they waited for the ambulance to arrive. He sadly spent 9 days in hospital recovering from this particular arc flash event. It's also not just a case of personnel injury, but also the amount of energy released means that you're going to inevitably see some equipment damage. In the best of cases, it might be an individual switchgear compartment that's affected. Some repairs might need to be made, but in the worst case, you might be losing entire sections of switchboard. Here's another fairly recent news story. This one was involved some DC equipment supporting railway electrification in the southeast of England. The arc flash occurred on a switchboard whilst a worker was changing out a small control fuse. So a very minor task, but led to this, a large fire, which, as you can see from the photo, basically gutted the entire switch room. The entire switchboard had to be removed, and of course all the equipment in here had to be removed, refurbished and refitted at a later date. So this was out of action for several months after the arc flash. So where can arc flash exist? Really, as I say, it's anywhere where there are exposed, energized electrical conductors. In the domestic setting in our houses, conductors are rarely exposed. There's a lot of insulation and safety requirements around that, but laboratory tests nevertheless have shown that arcs can be sustained with voltages as low as 208 volts AC. But really, it's much less likely to occur here in the domestic setting than it is in, say, commercial or industrial settings, where you've got 3-phase circuits, you've got higher voltages, more current, and that sort of thing. So this tends to be where we focus kind of more of the arc flash efforts. And on this slide is just a few examples of areas that we might look to for the arc flash hazard, from factories and waterworks, chemical plants. Places like data centers have a lot of electrical equipment and a lot of energy in them. We're also seeing things like private renewables. Solar farms are areas where arc flash can happen. And also large public buildings will have electrical distribution in them, so hospitals and universities, as well as maybe the more specialist sectors like the oil and gas offshore and the marine sector. To illustrate the fact that solar is one area where there can be concerns, this was reported very recently by CNBC in the States. Amazon shut down all of its North American rooftop solar systems in June 2021 after experiencing arc flash events at 6 out of 47 sites over a 12-month period. So a lot of arc flash events going on. Subsequent investigations found that there are issues with the design, the installation, and the maintenance of these systems, which were leading to these arc flashes and these fires occurring. Amazon themselves estimated that each of those 6 incidents cost around $2.7 million to investigate and rectify. So these are not small issues, and they're affecting big companies. For the most part, electrical systems that conform to our modern standards are well protected and insulated, especially when you've got all your covers in place and screens in place. They're there to prevent people from reaching the conducting parts. Of course, cables, bus duct and things like that are all insulated, so you tend to have less of a concern there. It is possible that an arc flash could be caused by dust or moisture building up inside equipment or over time as insulation degrades and fails. But this is the sort of thing that can only really be mitigated by things like inspection programs, preventative maintenance programs. What's much more likely to happen is that an arc flash is going to occur when you need to go into this equipment. You need to take the panels off, you need to expose the conductors to be able to do things like maintenance tasks, inspections, or perhaps fault finding. So it's these situations that really are the ones that should be considered most for arc flash. So here's just a quick example of opening up an electrical panel. This might be something you're presented with. And if you had to get into this to do some fault finding on the circuit breaker at the center here, the electrical switch, you've got exposed conductors then above and below you. So this is an area where if you've got potentially these are live on one side or both, an area where a drop tool or a piece of metal could come in contact, or a piece of test equipment could come in contact with these. When we think about medium voltage switchgear, this tends to be designed to try and keep those conducting parts and the live parts further back and away from the operator. So if someone's standing on the left-hand side of the equipment, a lot of the live equipment will be over further to the right. But nevertheless, even in this kind of equipment, you might have to get into the cable terminations to do some testing or inspection work, or you have the circuit breaker getting plugged into the spouts, which again is exposed copper work. So even in this type of equipment, there's still an arc flash potential there. Completely eliminating arc flash is unlikely. We've got live electricity as a crucial part of the modern world. Industrial and commercial premises have distribution throughout them to make everything work. Working dead is of course very important. It should always be the preferred option, but it's not always possible or practical, especially when you need to do fault finding or indeed proving the isolation of equipment. Arc flash statistics are kind of difficult to come across. Probably one of the main conclusions is that the most severe arc flashes tend to be thankfully quite rare, but it's really unknown how many arc flashes are happening within industry. They're not very well kind of broken out from the health and safety statistics that cover electricity as a whole. But anecdotally, we do know that that arc flashes occur. Research undertaken by a PPE manufacturer program found that 57% of UK electrical workers they had surveyed had first-hand experience of an arc flash incident, having experienced it themselves or witnessed it happening to someone else. And I think that aligns with our experience as well. The people who we've spoken to will see a similar rate. A lot of people will have had an arc flash happen to them or seen it happen to someone else at some point within their career. So it's definitely happening. There are solutions on the market which do reduce the arc flash likelihood or severity in equipment. This is referred to as arc resistant switchgear, and there's a couple of international standards which are shown on the screen here. One is for low voltage equipment and one is for medium voltage equipment. And this is really bringing in sort of inherently safe design and trying to design out some of the risks of arc flash. It might be about better insulation around conductors. It might be around channeling the arc flash energy away from the operator. It might be segregating the compartments better so that you have less of a buildup of energy. But of course, these kind of solutions really only apply to new equipment that you're going out and specifying today. It's a fairly recent addition to all the standards, so it's not something that you're really going to be able to add to legacy equipment that you already have on site. A good example of arc resistant switchgear is shown on the right under test. The switchboard is in the center here, and you can imagine that if someone's standing in front of the switchboard on the left-hand side and operating it, an arc flash occurs, and the design of this is such that the energy and the arc flash vapors and flames and heat is sent upwards and away from that person. So although this is not going to be a very nice experience to be standing there. It's better than having the arc flash directed straight at your face and chest, as we saw in the earlier videos. And of course, what we have to recognize is that the biggest influence on arc flash is the human factors. People make mistakes, people fail to recognize the hazard there, and they fail to take appropriate precautions. And it's these incidents which are, or these happenings are much more difficult to prevent without a more proactive approach to arc flash that's centered around giving people the knowledge and carrying out the risk assessment. A lot of cases you might have an arc resistant switchboard, but sometimes you have to defeat some of those protections in order to do the work that you need to do. So it's better to have both an arc flash strategy as well, potentially, as using arc rated equipment, if that's the best way to look at it. So one of the things to think about is arc flash covered under UK health and safety legislation? Is there something that should be driving us to kind of look at this hazard and recognize it? And the answer is yes. If you go into any switch room or any other workplace containing electrical equipment, you should find a poster like the one that's highlighted here, which details the Electricity at Work Regulations Act 1989. So it's a key set of regulations. It sits underneath the wider umbrella of the Health and Safety at Work Act 1974. And it puts duties on employers and employees in relation to working around electricity. And if you go into Regulation 2 interpretation of the regulations, then it defines a number of different hazards. And I've broken out the key ones on this slide here. So electric shock and electric burn, they're the ones that are associated with direct touch or direct contact with electricity. You touch a live conductor, the current passes through you to ground, and it does injury along the way. So electric shock obviously impacting the heart. Electric burn is subcutaneous burns as the current passes through your body. These are well understood. The hazard is recognized. It's brought attention to through signs and warnings. It's covered by risk assessment. People take the appropriate precautions to deal with these kind of hazards. So those ones are sort of well understood and managed. On the other end of the scale, we've got the fire or explosion initiated by electricity, and this is really where you've got a spark lighting a gas cloud and causing a major accident hazard. So we have things like DESIA and PFIA and the use of appropriate equipment in explosive atmospheres to deal with that one. So that really leaves the fourth one, which is electrical explosion or arcing, and that's really that's what we're discussing today in this webinar. So it's called out as one of the key hazards within the regulations. And if you have a look at some of the supporting, the guidance to the regulations, the safe working practice documents that the HSE publish, they go into more detail about arc flashover. There's lots of different terms that get used, but it's all talking about arc flash. It's all talking about burns as a result of the arc flash. And it mentioned particularly in HSG 85, the safe working practices, that people often don't appreciate the risk of serious injury that can arise from arcing. So it's definitely called out within these key pieces of legislation. And therefore, because it's called out as a hazard, there's an obligation to put in place, take the suitable and sufficient risk assessment and put into place the mitigations that are needed to make sure that people don't unnecessarily come to harm from this hazard. UK legislation, I'm sure we're all aware, tends to be less prescriptive in how you meet those obligations. As a bit of a contrast, you often hear that arc flash is sort of quite a big topic and quite a hot topic in the States. Over there, they have their standard for electrical safety in the workplace, which is called NFPA 70E, this document here. And this really lays out a very clearly defined way to identify, risk assess, and mitigate arc flash. In the UK, we don't have maybe such a strong equivalent. You do hear people referring to adopting the NFPA 70E approach, But the good news is that there are ongoing efforts to codify arc flash in the UK. A recent development is this publication from the Institute of Engineering and Technology, an arc flash risk management guide, which does provide a structured approach to arc flash and kind of brings together a lot of best practice and is well aligned with the American approach. So arc flash, it should be managed like any other hazard that you encounter on site. So stepping through a risk assessment process, determining the mitigation measures and giving people the knowledge and the supporting materials to implement those mitigation measures. And of course, a successful arc flash strategy is one that's simple for those working on site to adopt. Just to kind of reinforce this message, a final point in this section, another news story again from just a few weeks ago in July, the retailer B&M were fined £1 million for breaches of the Health and Safety at Work Act after an electrician, a third-party contractor working on one of their warehouses near Liverpool, experienced an arc flash after touching live conducting parts with a metal spanner. He suffered from burns to 15% of his body. He ended up in a medically induced coma for a fortnight. So again, a very serious incident. So B&M themselves, as the site owner and duty holder, they were fined heavily. The third-party contractor would also have been fined quite heavily for this, but they'd already ceased trading because their insurance premiums had shot through the roof following the accident. And the HSE kind of called out, failures to appoint competent persons, failures to recognise the severity of the hazard in this case. So the final main part of the webinar really is to consider how can we go about putting in place an arc flash strategy, and how can we demonstrate that we're managing the arc flash hazard at site. There's kind of different approaches to this, but we look at developing an arc flash strategy in terms of these key 3 steps. That is predict, prevent, and protect. The webinar, I'll necessarily kind of focus on predict. It's sort of the stage that has the most aspects to begin with, but I will touch briefly on prevent and protect towards the end. They are obviously important, but we'll focus on predict for the purposes of this webinar. So really predict is all about this risk assessment process, and I'm sure many people attending today are familiar with this. It's the general approach to risk assessment. First of all, we're going to be identifying where the arc flash hazard exists on site. So this requires, I guess, an understanding of your electrical equipment, who's completing work on it, and what kinds of work is done and how often it's done. It's recommended, if you're not a sort of an electrical bias person, to take a walk around site with someone who is, maybe one of your electrical technicians or an authorized person, and look for occasions, particularly where electrical equipment is going to be opened up. Those covers are going to be removed, doors taken off, panels opened, and particularly where de-energization is impractical. You want to think about routine tasks that are happening, like isolation and de-isolation of circuits. But you also want to think about those tasks that maybe only happen every 4 or 5 years. Perhaps for one particular piece of maintenance work, a temporary generator is tied in, but that only happens every so often. You need to think about those kind of things as well. They might kind of catch you out if they're not at the front of everyone's mind. And then, of course, once you know and have identified the arc flash hazards, it's a case of risk assessing them. And the usual approach is determining the severity of the arc flash and the likelihood of an arc flash event happening at any one particular piece of equipment. It's important to note, especially with severity, really any arc flash is dangerous to someone standing in front of the switchboard if that happens to them. But it's important to get an idea of the varying levels of severity across the different equipment, because you're going to want to focus your efforts on hazard reduction, and it also helps you choose an appropriately rated set of PPE at the end of the day. So severity is most accurately determined these days by getting what's called an arc flash study undertaken. In simple terms, this means you take a computer model of your network and you complete calculations based on an internationally recognized standard to calculate the thermal energy released by an arc. The thermal energy is really what we focus on. There are obviously other effects of the arc, but the thermal energy is the one that really kind of takes precedence. For commercial and industrial premises, the most widely used methodology for this calculation is what's called IEEE 1584. This document was last updated in 2018, so it's a recently updated standard. It's developed in the United States. The IEEE working group for this commissioned thousands of laboratory arc flash tests to generate a whole bunch of empirical data around the energy released by arcs under different voltages and currents and equipment configurations. And bringing all this data together allowed them to then statistically analyze it and develop a set of equations that allow for extrapolation, interpolation to apply these to a wide range of electrical equipment, including UK equipment. It's perfectly applicable here. The equations then have been built into popular electrical power analysis software, which allows for arc flash calculations to be run on a computer alongside your other system studies like load flow and short circuit. It's worth mentioning that the 1584 standard does have some limitations. It only goes up to 15 kV. So this tends to be, in our experience, this covers a lot of the commercial and industrial systems out there. But if you do have a system that's operating higher than that, some equipment on site that's operating above 15 kV, there are alternative methodologies that are available to look at that. There's a number of inputs to an arc flash study, and realistically gathering the data and building up the system model is usually the thing that takes the most amount of time. It can be a real time sink depending on how well documented the site is and how readily accessible information is. Even for the simple system that's shown on the screen now, you can be looking at quite a lot of data gathering for things like the site supply, transformers, generators, the switchgear themselves and cables. A crucial piece of information is your overcurrent protection settings for relays or the ratings of your fuses. This is one of the big drivers of arc flash incident energy. That might be in a schedule somewhere, but equally it might be something that's out of date, so you need to go out and do a full survey of equipment on your site. And realistically, you also need to think about different configurations of the network. This can really change how the arc flash energy works, depending on whether you're using local generation, relying on the site supply, have multiple sources feeding a different point, and things like that. And what you can see is the green arrow is the circuit breaker that they were closing, that Scott and Sam were closing in our incident example. But to understand specifically what happens at that breaker, you need to have a good understanding of the whole of this network. And so that's where the time often comes. So once the study is done, all that data is processed and the calculations are run, you're going to get given some results. And the two key things that you're going to be told about in terms of severity are your incident energy and your arc flash boundary at each of these pieces of equipment. On the screen is a simplified set of results. Basically, we've just distilled it down to the important information, and this shows it for two different scenarios: the normal, where you're fed from your site supply, from your external grid, and a standby scenario where maybe that has been lost, so you've switched over to the standby generator. And it's important to take into account, as I say, these different scenarios. You can see that for the LV distribution, the incident energy is quite different between the two scenarios. The fault current characteristics of the standby generator are quite different to in the normal scenario. So it's important to capture that kind of detail. Now, those two values I mentioned are important. The incident energy expresses the thermal energy at the worker's head and torso. So although your hand might be very close to where the arc happens, you actually calculate the incident energy and the sort of the severity of the arc a distance away, and that's because protecting the head and torso is the most important in terms of protecting vital organs. This distance, the distance away from the arc, is called the working distance. So that is something that you set for each piece of equipment depending on the activity. Sometimes it's a standard distance for a piece of equipment, but you also want to look at what your people are doing. The arc flash boundary is the second piece of important information that you get out of a study, and that expresses the distance at which you can imagine the arc is happening in the panel here at the energized electrical conductor. The arc happens and the energy dissipates out and it spreads out and drops off as you get further away from where the arc happened. And as it drops to a point which is considered acceptably low, this is the arc flash boundary. It's got a value of 1.2 calories per centimeter squared, which is about the equivalent of holding your skin up to a burning candle. So it's not, you don't want to hold it there for very long, but it's going to be an injury that you can recover from. So it's important to recognize these two kind of important factors, that you've got this working distance set and that the energy is dissipating away to a point where it's considered acceptably low. So once you've got your severity, then you need to think about likelihood. This is a bit more, I guess, of a subjective assessment. The thing with the arc flash study is it gives you numbers that you can use in the risk assessment. Likelihood is a bit more subjective, but it's about considering what the switch room, how the switch room's used, the condition and maybe the age of your equipment, and the types and frequencies that are going on. So just to pick out a couple of examples in the table at the moment, maybe the high voltage switchboard is a new switchboard. It was only installed last year, and it's installed in its own switch room, which is locked and inaccessible to anyone other than those authorized to go in there. So you might consider that to be a low likelihood of an arc flash happening and impacting people. Whereas the LV distribution switchboard, that is sitting in a much more populated area of the site. There's more people coming and going, and generally more tasks happen on that switchboard. So you might consider that to be a more high likelihood of an arc flash happening. And bringing that all together, you're then bringing your severity and likelihood together to get a risk for each of those pieces of equipment within those two different scenarios. And you can see that probably what you're going to find is you're going to get quite a spread of risks across a site. You're going to find some instances of high risk, some instances of low risk, and it's best at this stage to work with maybe a consultant to define what you're going to consider the ALARP risk level for your site, because this is going to help you make some informed decisions then about risk reduction. One approach that a lot of our clients have found useful to simplify this a little bit is to use the concept of a threshold incident energy level. So for example, you could say 12 calories per centimeter is going to be our threshold value, and then anything above that you want to try and take measures to bring it below the threshold. And then anything below the threshold is then something that then can be managed through mitigation measures around knowledge, training, competency, risk assessments, and the use of PPE, because you've got a generally lower incident energy at that point. So that's one such strategy to try and simplify this and make this a kind of a workable proposition for a site, rather than having incident energies all over the place and different risk levels, and people are a bit unsure about exactly what they need to be doing and when. So that really kind of wraps up the idea of predict. And then prevent is really identifying the mitigation measures that can be put into place. I'm not going to spend too much time dwelling on this slide. Hopefully what you can take from the right-hand side is that within each of these categories, within the hierarchy of controls, there are a number of different options available for arc flash mitigation. It's probably worth mentioning that, especially if you're in kind of your elimination substitution, the engineering controls, these are going to be solutions that are going to involve help from a specialist in electrical protection or maybe in switchgear to help you implement those. I'll give you one such example. This is within the substitution category from the hierarchy of risk controls. And this is something called a maintenance mode key switch. It's quite a popular mitigation measure. And basically what it means is that you're temporarily going to make your overcurrent protection more sensitive to a trip. So if an arc flash does occur, the the protection is going to recognize that very, very quickly, trip the circuit breaker, and therefore keep your incident energy down as much as possible. So you can see in this particular example, it might go from 0.6 second trip time in normal mode to 0.06 seconds in maintenance mode, reducing that incident energy by quite a lot. So this is quite a popular sort of almost a retrofit option for existing switchboards. With Arc Flash, you tend to find that there's always some residual risk. And so Arc Flash PPE is more often than not adopted for activities on or around live equipment. Arc Flash PPE is primarily there to mitigate against the thermal effects of the Arc Flash. And it's available from a number of different manufacturers. What it typically comes with is a rating helpfully given in calories per centimeter squared, which is a number determined through laboratory testing. There's a lot that could be said about Arc Flash PPE. Again, it's a whole sort of webinar topic in and of itself, but really what you need to be looking for is that the Arc Flash PPE has a rating exceeding the incident energy that you've calculated as part of your Arc Flash study. That's the thing, you want more protection than the Arc can produce, basically, to make sure that you limit the possibility of injury. And it's also worth bearing in mind that you don't want to be burdening workers with overly heavy or restrictive PPE, because this can make tasks more difficult or even unsafe. And it means that the PPE doesn't get worn out of frustration or inconvenience. So this is why it's important to think about bringing the hazard down as much as you can as the first step, to try and get the incident energy down so that you're reducing the burden of what the PPE has to handle, basically. So just to wrap up that prevent step, what you might do is go through a few iterations and come up with a few different strategies to bring down some of these highs and mediums down to a more acceptable risk level. So say at the LV distribution, you identify that one of these maintenance mode systems would be the best way to deal with that high incident energy. And that then allows you to make a sensible selection of PPE across the site, which brings down that residual risk. And that then means that you can then roll into protect, which means rolling out that Arc Flash strategy, of course. It means clearly documenting it in your site safety rules and procedures, and ensuring that people have the training and the competence to make it work. And of course, it's not something that you just roll out and leave. You should be monitoring it and improving it. And also, if you make changes to your system, if more switchgear is added, more motors are added, or a generator is added, this is something that can change the Arc Flash values. So you really should be thinking about revalidating the numbers and revisiting how your strategy works in those situations. So to conclude, I think I just want to run that opening scenario again, but this time with the benefit of an Arc Flash strategy in place. So this time at the morning permit meeting, the task of closing up this circuit breaker is reviewed, and along with electric shock and the risks, it's recognized that this is a situation where Arc Flash could occur. The switchboard is going to be opened up. Effectively, there's an opening in the switchboard, and there's those live parts at the back, which people are going to be close by. So this is definitely a case where an Arc Flash could occur. So you risk assess this, and the site electrical safety procedures are consulted, and it's determined that you've got the maintenance mode available on this particular switchboard. So you should activate that before any intrusive works commence. If you've got that active, then the site standard Arc Flash PPE, which is rated for 12 calories per centimeter squared, is fine for this task. The Arc Flash boundary for this particular switchboard has been set at 5 meters, so that should be marked or barriered off in some way. And any person not involved in the task should remain, well away, well beyond the Arc Flash boundary. Down at the switchboard, the risk assessment's reviewed. There's actually some labeling now on the equipment, and this confirms the findings of the risk assessment and identifies those mitigations. So Scott goes away and he turns on the maintenance mode by turning on this key switch adjacent to the switchboard, and then he and Sam, they put on their balaclavas, they put on a face shield, and they add some gloves to the daily wear Arc Flash PPE coveralls that they're already wearing. You're not involved in the task, so you're asked to stand well back beyond that 5 meter line and told to make sure no one comes any closer. So this time, the task goes ahead, the breaker jams, but this time when it's shoved, there's that same bright metallic ping, which is immediately followed by a brief flash of white light. But this time there's just maybe a lick of flames and a puff of smoke, and almost simultaneously the entire switchboard trips. Scott, who was pushing the breaker in at the time, he steps back, he looks a little bit stunned. His PPE maybe shows a bit of light scorching to the arms, but otherwise he's unharmed. He says to Sam, "Blimey, that was close. Looks like there's probably a flashover or something behind the breaker. I guess we best get the tools out. It's going to be a long weekend." So the compressor house isn't going to be starting up today, but both Sam and Scott are uninjured, and the damage to the breaker from the arc is minimal. They're going to have to investigate, they'll make a repair, but the rest of the switchboard is largely unaffected. Having the mitigations in place has prevented harm to the electricians, and it's limited equipment damage from the arc flash. So just in summary, what have we kind of covered today? Arc flash is a hazard associated with live electrical equipment in commercial and industrial workplaces. It can cause severe burns, it can cause equipment damage. It's called out as a specific hazard by UK health and safety legislation. So that means that there is a need to identify that hazard where it exists on your site and put in place those mitigations to make sure that the injury is limited as far as it can be, as far as practical. So arc flash should be incorporated into site safety and risk assessment procedures, just like any other hazard that you've identified. And as we've shown, hopefully it can be risk assessed, and there's a procedure that can be followed, or a process that can be followed to do that, to identify the risk mitigation measures and roll that out to site to provide protection to people and equipment. So even though an arc flash can be over in less than a second, the consequences of it going wrong can last a lifetime. So finally, hopefully I want you to take a few things away from this session and think about what we've covered. Be useful to take a walk around your electrical equipment if you are on site-based. Consider where you might have an arc flash hazard on site. It's worth thinking about, do you have a set of electrical safety rules that arc flash can be incorporated into? And it's also worth thinking about, are you demonstrating that you've adequately addressed the electrical arc flash hazard? So I will leave it there. Thank you very much for your time. I'll just put a few kind of contact details up on the slide here. But as George said at the beginning, we're very happy to take any questions.
Thanks very much for that, Nick. Very illuminating. So we had a couple of questions during the webinar earlier on. I'll read them out so I'll make sure everyone can see them and can hear the responses. So first one was, what suitable PPE do we have to protect workers from getting electrocuted? I've responded to this one during the webinar just to try and differentiate between electrocution or electric shock and arc flash. Two separate hazards we need to consider when working with electrical equipment. What we're covering here is arc flash, which isn't direct contact with electricity, but is several sort of effects or hazards associated with a flashover, which Nick discussed earlier in the presentation. And there are PPE options, as was briefly covered. We might have mentioned that PPE could be a webinar on its own, and there have been ones done by specialist PPE providers. There are a number that operate in the UK which are quite good reputations and can provide options in that. If you want any more details of arc flash PPE suppliers, feel free to get in touch with us and we can put you on to someone that can help you. The second question that came in was, how often should a company conduct electrical facility audits? It's a bit more of a generalized question. Suggested that depends on your system, depends how well developed your processes and procedures are around electrical safety. If you're unsure on that, your best bet would be to get in touch with an electrical safety consultant and bring them in to do an initial audit, which will show you where gaps between what you have and where you want to go. But beyond that, if it is well documented and it's a system that works well, an audit every 2 years would be prudent and sort of a good timeline between one audit and the next. In terms of arc flash, We tend to fall in line with the NFPA 70E guidelines, which are to revisit your ARC Flash study every 5 years to see what could have changed on your site. But also if you have any significant changes that happen, for example, if you replace a switchboard, introduce or remove any generation or sources of short circuit fault current, then that is a good time to just rerun your ARC Flash calculations to see if there have been any significant changes to your risks. So we had some other questions come in at the end after Nick's presentation. So one here on, do we get the presentation? I think the answer is yes. Julie might be able to jump in and confirm that, but I think the presentation should be made available following this, and it is being recorded if I'm right. So this will be available to watch later.
Yes, it will be. Yeah, it'll be uploaded onto our YouTube channel. And if you want to let me have a copy of your presentation, if anybody would like a copy, if you just email branches@IIRSM.org and I'll arrange for that to be sent to you.
Great. Okay, we'll put that email address in the response to the question so people have it. And yes, the webinar's up on YouTube, so you're a YouTube star now, Nick, which is good. Question here, any specific measures for a person with medical conditions or undisclosed health issues? Also, any impacts of persons with steel rods, I guess that is, or a pacemaker. So I guess that's around underlying health issues and any impact of ARC Flash or PPE.
Yeah, that's a good question. I suppose, I mean, that would also tie into electric shock as well. It's going to be sort of similar issues. So I think if there's things available for those kind of people, then it would be similar. You know, ARC Flash is, as Callum said, it's a little bit different. It's not direct contact with electricity, but obviously you're working around live conductors. So whatever kind of precautions are already in place for that would continue to apply. And then the ARC Flash PP is something that you're building on top of the shock risk effectively.
Yeah, and from an ARC Flash PPE point of view, we don't have any restrictions that would affect someone with a condition like this. But again, it should be something considered during risk assessment on a case-by-case basis.
Yes.
So one here is more of a statement, a good webinar I've ever attended so far, so good feedback for you, Nick, there. And can GFCI or ALCB, so ground fault protection, can this prevent ARC flashes from occurring?
Another good question. Really, it's your overcurrent protection that is your primary protection against this, because ARC flash is a little bit difficult. It's kind of a highly dynamic phenomenon, which can evolve. The type of fault that it can appear as and can manifest as can develop as an ARC flash continues, and as it gets worse and worse and does more and more equipment damage. So what we tend to find is that it maybe starts off as a phase-to-phase fault, but rapidly spreads to become a three-phase fault, and then might find a path to earth as more and more damage and things are done. So really, primarily, you're looking for the fault current flow that's associated with an ARC flash. An ARC flash kind of characteristically looks a lot like a short circuit, and that's where your overcurrent protection is looking after you. And the best is to have instantaneous overcurrent protection. That gives you your fastest trip times. And so what you tend to find is that a lot of the dedicated ARC flash detection devices are doing something around making the trip time as short as possible, and they're then often using other things, so detecting the light flash from the ARC flash and combining that with some information around what the current is doing to get it tripped as quickly as possible. So yeah, I'd really say that it's kind of a focus on your overcurrent protection rather than any other protective devices.
Good, thanks, Nick. A couple have come directly through to me. So the first one here is there training that can be given to staff on ARC Flash?
Yes, yes. There is training out there. There's a lot of sort of companies offering, or there's a few companies in the UK offering awareness courses for training. which probably take a similar sort of agenda as what we've covered today, really, maybe expand it over a few more hours and go into a bit more in depth around the calculations and things like that. What we tend to offer, if we're talking to a company specifically, is training that specifically suits the company and suits the Arc Flash risk and the Arc Flash strategy that they've decided to adopt on site. So we can take into account, you've selected these kind of mitigation measures, you have your task risk assessments arranged in such a way, these are the type of labels that we've applied to your equipment, this is the type of PPE that's going to be used. We tend to find that it's more valuable to have a specifically focused training course than the more general awareness training courses.
Yeah, okay. Good, thanks, Nick. And the last one I have in here was, so how long does it take to complete an Arc Flash study? And a second part of this is, what are the outputs from the study?
Yeah, so another really good question. I think I maybe alluded to it in the presentation, but the data gathering is really what takes a lot of the time. I think someone's estimated, in a typical study, it can be 60–70% of your effort is actually spent gathering data and building the model. And once you've got that model up and running, actually running the results and pulling a report together is not requiring that much time. So I'd say for us, for a facility, for sort of a typical industrial facility, a HV switchboard distributing out maybe through a ring main to a number of LV substations, we're looking at having to gather all that data and process that data, lots of back and forth with the client, and then pulling everything together is maybe somewhere in the 5 to 6 week region. Obviously, as your facility scales and there's more data and things, it just becomes more complex and takes longer. And in terms of output, what we pull together is a comprehensive report. The key parts are bringing out those incident energies and the Arc Flash boundaries. Those are those kind of the qualitative numbers that you get out of an Arc Flash study. So that's giving you that severity piece. And we also then, if we're given the opportunity, especially to visit sites and have a walk around your switch room and talk to people, then we put together the likelihood as well, and that gives us that overall risk rating. And then it's really a case of how those first sets of results look like. It might be that you've got generally quite low results for incident energy and likelihood, so you might be able to jump straight into a selection of PPE, incorporating it into risk assessments. But sometimes we find that you've got some quite high incident energies, and that's where you want to take a step back and say, okay, what can we do to get those incident energies down before we fully commit to PPE selection and things like that. It's worth bearing in mind, quite a lot of the time you can make simple changes to your overcurrent protection and make some quite significant improvements in incident energy just by tweaking some of the settings which have maybe not been touched since day one on a site. You can maybe tweak your instantaneous settings in quite a few places and get those numbers down. So how an Arc Flash strategy kind of evolves, it can go down a few different routes, but it's really a case of understanding what your initial risk profile looks like and then making some sensible decisions from that point.
Good, thanks, Nick. And the last one that was just entered was just some feedback again. So bravo, excellent presentation, well executed, and I like the practical examples and video examples. Thanks for the feedback there. But that is the last one there. So Julie, are you going to come back in to close? We're almost
yes,
at the hour
I
mark,
will
so
do. Thank you so much for really, you obviously know your stuff, Nick. Even I could understand what you were talking about. I found it really enjoyable. Thank you, as I'm sure most of the attendees did. So I'd like to thank you both for your time that you've given up to present on behalf of the Scotland branch. I'd like to thank everyone for attending and let people know that it will be on the YouTube channel in the next couple of days, and your attendance certificates will come out this time tomorrow. So I'd like to wish everyone a good afternoon or a good evening wherever you are in the world. Goodbye, everyone.